Hello, welcome to another module in this massive open online course on the principles of CDMA, MIMO, OFDM wireless communication systems. So currently we are looking at the principles with the various techniques and the theory behind MIMO wireless communication systems. Today let us look at a new aspect, let us look at a specific a special case of MIMO wireless communication systems, that is MISO wireless communication system. Today's module, let us start looking at MISO wireless communication systems, that is multiple input single multiple input single output system. And we have already seen this before. Multiple input single output systems means you have multiple transmit antennas and a single output, that is a single receive antenna. So by definition these systems have multiple inputs, that is multiple transmit or multiple TX antennas and a single receive antenna or a single output antenna. In particular, what we are going to be interested in these systems is what is known as a new technique, that is known as transmit beamforming. We have previously seen maximum ratio combining at the receiver for a single input multiple output system, that is for a single input multiple output system we have maximal ratio combining, which is also known as receive beamforming. Now if we have multiple inputs and a single output, we can do something known as transmit beamforming, and this is what we are going to explore in this module. So let us start by looking at a simple example. Let us consider a simple example in which we have a transmitter with two transmit antennas and a receiver. So I have a transmitter with two transmit antennas and I have a receiver with a single receive antenna, right, and therefore I have two transmit antennas, a single receive antenna. Let me write that down here, two transmit antennas and one receive antenna, and therefore let H1 denote the channel coefficient between H1 denote the channel coefficient between transmit antenna 1 and the receive antenna, and simultaneously H2 denote the channel coefficient between transmit antenna 2 and the receive antenna. Therefore the model for this MISO system, model for, in fact this is a 1 cross 2 MISO system. This is a 1 cross 2 MISO system, and the model for this is the received symbol Y equals the 1 cross 2 channel H1 H2 times the transmitted vector x1 x2 plus W. So what do we have over here? We have an R cross 1, which is basically 1 cross 1 received symbol. This is my 1 cross 2 channel vector, the MISO channel vector. This is my T cross 1 or 2 cross 1 transmit vector, and this is my R cross 1 or 1 cross 1 noise. And similar to before, no surprises here, we will assume Gaussian noise with mean 0 and variance sigma square. So W is Gaussian noise with mean 0 variance sigma square. received symbol y is a single symbol 1 cross 1, the channel vector h1 h2 is the 1 cross 2, that is r cross t MISO channel vector, and x1 x2 is the 2 cross 1 or t cross 1 transmit symbol vector in this MISO system. Now, let us look at what is the appropriate transmission scheme for this MISO system. For this MISO system, one can ask the question, what is the appropriate transmission scheme? So, we have x bar is the transmit vector, this is our transmit vector. This is our transmit vector x bar, out of which I have x1 is the symbol on transmit antenna and x2 is the symbol on transmit antenna 2. And one can ask the question, what is the optimal or what is the best, what is the optimal transmission scheme for this MISO system? So, let us start with the transmit symbol x. Let x denote a transmit, a single transmit symbol. Let x denote a single transmit symbol, then the vector x bar can be formed as the transmit vector x bar is given as, well, 1 over norm of h bar, vector h bar times h1 conjugate, h2 conjugate, h1 conjugate, h2 conjugate times my transmit symbol x. So, what do I have over here? X bar is the transmit vector, my x is the transmit symbol, and this norm of h bar is obviously my norm of h bar, this is equal to square root of magnitude h1 square plus magnitude h2 square, and this vector which you are looking at here, that is h1 conjugate h2 conjugate divided by norm h bar, this is known as the transmit beamformer. This is known as the transmit beamformer. So, this vector that you are seeing over here, that is h1 conjugate h2 conjugate, the vector divided by norm of h bar, this is a unit vector, you can check that the norm of this vector is unity, this is known as the transmit beamformer. What this means is you are forming a beam in the direction given by this unit vector. So, x is the symbol that is being transmitted, it is being transmitted in the direction of this transmit beamformer, therefore, this scheme is also known as the transmit beamforming scheme. Alright. So, this vector, so what is my transmit beamformer? Let me write it clearly, the transmit beamformer equals 1 over norm h bar times h1 conjugate h2 conjugate. So, this is a unit vector. So, firstly this is a unit vector, the norm of this vector is unity, and this is known as the transmit beamformer for this system. This is the transmit beamformer for this system, and this scheme is known as transmit beamforming. Now, let us look at what is the output y going to be once we employ this transmit beamforming scheme. So, when we employ the transmit beamforming scheme, therefore, what we are saying is x bar, or what we are saying is x bar equals H1 conjugate divided by norm of H bar into x1, H2 conjugate divided by norm H bar into x2. Therefore, or sorry, x times x, and therefore, what we are saying is symbol from TX antenna 1, we are transmitting H1 conjugate x divided by norm H bar, from TX antenna 2, we are transmitting H2 conjugate x divided by norm H bar, and therefore, what we have is basically at the receiver what we have is we are going to have y equals H1 H2 times H1 conjugate H2 conjugate H1 conjugate H2 conjugate times 1 divided by norm H bar times x plus w. Now, if you can see this H1 into H1 conjugate plus H2 into H2 conjugate is norm H square divided by norm of H. So, this is going to be equal to norm of H bar times x plus w. And very interestingly, what you see here is now if I compute the SNR of this scheme, I am going to have SNR is equal to norm H bar square expected magnitude x square divided by variance of the noise sigma square, which is equal to norm H bar square P divided by sigma square, and you will see that this is exactly the same SNR as MRC or maximal ratio combining. This is exactly the same SNR as MRC, right. So, transmit beamforming, when we transmit beamform in the direction of H1 conjugate H2 conjugate divided by norm of H bar, the SNR at the receiver is the same as what we get for maximum ratio combining, that is with transmit antennas at the receiver, multiple antennas at the transmitter and single antenna at the receiver, we are able to achieve the same SNR as a scheme with multiple antennas at the receiver and a single antenna at the transmitter. So, transmit beamforming is able to achieve the same SNR as maximal ratio combining, right. However, if you notice what we are transmitting the transmit vector equals H1 conjugate H2 conjugate 1 divided by norm of h bar times x. So, what we need at the transmitter, we need knowledge of these fading coefficients h1, h2 to form the transmit beamformer, right. So, which means we need knowledge of the channel coefficients or the channel state at the transmitter. This is also known as the channel state information, and frequently this is difficult to obtain in a wireless communication system at the transmitter. So, this is the challenge in transmit beamforming. The challenge in transmit beamforming is basically the channel coefficients or channel state is to be known the channel state is known to be known at the transmitter. This is channel coefficients or channel state. This is also known as channel state information, CSI, which is channel state information. That is what we are saying is for maximal ratio transmission, for maximum ratio transmission or for transmit beamforming, CSI is or channel state information is required at transmitter, and this is challenging. That is for CSI, for the channel state information to be known at the transmitter is challenging. So, maximum ratio transmission is transmit beamforming is possible only when the channel state information is available. Channel state information or the knowledge of the channel coefficients h1, h2 is available at the transmitter. Now, what happens when the channel coefficients h1, h2 are not known at the transmitter? Then we have to explore alternative schemes. One such scheme is known as space time coding, which is something that we are going to look at in the subsequent modules. So, for transmit beamforming is optimal in the sense it yields the same SNR as maximal ratio combining. However, it is also challenging to implement because the channel state information is required at the transmitter. So, this is the summary of this transmit beamforming scheme. Now, let us try to look at a simple example to understand this transmit beamforming. Let us try to look at a simple example to understand this transmit beamforming. So, consider a 1x2 MISO system. Now, in this 1x2 MISO system, let our system model be given as y equals 2 plus j and 1 minus 2j times x1, x2 plus w. So, basically what we are saying is our h1, this is our h1, this is our h2, which means our h1 equals 2 plus j, our h2 equals 1 minus 2j, and we are asking what is the optimal transmit beamforming procedure. What is optimal transmit beamforming. If CSI is available, or if CSI is available, or if channel state information is available at the transmitter, that is for this system, what is the optimal transmit beamforming procedure when the channel state information is available at the transmitter or the channel coefficients are known at the transmitter. Obviously, the optimal procedure is transmit beamforming, and the transmit beamformer is X bar equals H1 conjugate H2 conjugate 1 divided by norm H bar times X. Now, let us look at, now we have H1 equals 2 plus J, H2 equals 1 minus 2J, therefore, norm H bar equals square root of 4 plus 1 magnitude H1 square plus 1 plus 4, that is magnitude H2 square, which is square root of 10, and therefore, the optimal transmit vector X bar equals, this is equal to 1 divided by square root of, this is equal to 1 divided by square root of 10 times H1 conjugate, that is 2 minus J, H2 conjugate, that is 1 minus 2J times X. So, optimal transmit vector in this scenario is X bar equal to 1 over square root of 10 times 2 minus J 1 minus 2J into the transmit symbol X. So, X is the transmit symbol in this scenario. Now, let us substitute this transmit vector in the system model to see what is the SNR that we obtain. So, once I substitute this transmit vector, I obtain Y equals 2 plus J into 1 plus 2J times 2 minus J into 1 minus 2J times 1 over square root of 10 into X plus W, and you can see this is 2 plus J into 2 minus J, which is basically 2 plus J into 2 minus J, which is basically 5 plus 1 plus 2J into Y minus 2J, which is 5. So, 5 plus 5 10 divided by square root of 10. So, I get square root of 10 times X plus W, and square root of 10 is basically nothing but norm H bar. So, the SNR equals 10 times P divided by sigma square, which is the same thing as norm H bar square P divided by sigma square, and this is the same as SNR with maximum ratio. So, what we are saying is that the SNR at the receiver is 10 times P over sigma square, which is the same as norm H bar square P over sigma square, which is the same as the SNR with maximum ratio combining. So, transmit beamforming is achieving the same SNR as maximum ratio combining. And now, it is also straightforward to compute the bit error rate of this system, all right. So, let us look at the bit error rate of this system. Let us look at the bit error rate of let us look at the bit error rate of transmit beamforming. Now, before that we will extend this to L antennas. Transmit beamforming can naturally be extended to L antennas. Transmit beamforming can be extended transmit beamforming can be extended to a general scenario with L antennas. So, let us say I have a 1 cross L MISO system y equals H1, H2, HL times X1, X2 up to XL plus W, which is basically H bar transpose X bar plus W. So, what I have is Y equals H bar transpose X bar plus W. H bar transpose is my 1 cross L channel vector, X bar is my L cross 1 transmit vector, this is my 1 cross 1 Gaussian noise mean 0 variance sigma square as usual. And then what I am going to transmit with my transmit beamformer is X bar equals 1 over norm H bar times H bar conjugate times X, where X is the, this is my transmit symbol. So, X is my transmit symbol. So, my system model is Y equals H bar transpose X plus W. My transmit beamformer is H conjugate, H bar conjugate divided by norm H bar, and my vector, transmit vector is X bar equals H bar conjugate divided by norm H bar times X. Therefore, once I substitute this in the system model, I get Y equals H bar transpose H bar conjugate divided by norm H bar times X plus W. Now, H bar transpose norm H bar transpose H bar conjugate equals norm H bar square divided by norm H bar, which gives me H bar X plus W, and therefore, my SNR goes norm H bar square P divided by sigma square. This is the same as MRC. SNR is equal to MRC. Therefore, the bit error rate performance of transmit beamforming is identical to that of MRC. Since the SNR is identical to that of MRC, the bit error rate for transmit beamforming is identical to that of maximal ratio combining. So, therefore, bit error rate of transmit beamforming is identical to that of MRC, which means at high SNR the bit error rate equals 2L minus 1 choose L 1 over 2 SNR raised to the power of L, where L is the number of transmit antennas. Where L is the number of transmit antennas. So, bit error rate at high SNR is 2L minus 1 choose L 1 over 2 SNR raised to the power of L, where L is the number of transmit antennas. That is similar to the bit error rate of maximal ratio combining at high SNR. Okay. So, basically since the SNR is identical to that of MRC, the bit error rate performance is also identical to that of MRC, except the procedure is different. There we perform maximal ratio combining at the receiver, here we have to perform transmit beamforming at the transmitter. So, the procedure is different, the challenge is different, because in transmit beamforming you need knowledge of the channel coefficients at the transmitter. However, If we are able to do that, then the ensuing performance and the bit error rate is identical to that of MRC, because at the end of the day the SNR is basically identical in both these schemes. So, let us do a simple example again to understand this thing. It is a very simple example. Consider a 1×3 MISO system consider a 1×3 MISO system and SNR equals 25 dB. Question we want to ask is what is the average bit error rate of this system. The bit error rate equals 2L minus 1, choose L 1 over twice SNR raised to the power of 3. Now, L is equal to 3, 2L minus 1, choose L equals 5, choose 3, which is equal to 10. So, the bit error rate is basically equal to 10 divided by 8, 1 over SNR raised to the power of 3. Now, SNR in dB equals 25 dB, right, that is what we have said, the dB SNR dB equals 25 dB, which means 10 log 10 SNR equals 25, which means SNR equals 10 to the power of 2.5. Therefore, the bit error rate equals 10 divided by 8 times 1 over 10 divided by 8 divided by 10 to the power of 2.5, 1 over SNR 10 to the power of 2.5 to 3, and that is equal to, that is basically equal to, well, that is approximately 6.3 into 10 to the power of minus 8. So, that is the approximate, that is the bit error rate of this system at high SNR, that is 10 over 8 times 1 over SNR cube, which is approximately 6.3 into 10 to the power of minus 8. So, that is the bit error rate of this system with transmit beamforming. So, what we have seen in this module is we have seen an interesting case of what happens with multiple transmit antennas at the what we have seen so far in the previous modules. In fact, in the very early part of this course, when we have multiple receive antennas at the receiver and a single transmit antenna. Now, we have seen the other side of it, that is when we have the analogous case when you have multiple transmit antennas at the transmitter and a single receive antenna, that is a MISO system, multiple input single output system. In this system, the optimal transmission scheme is transmit beamforming, and transmit beamforming achieves a performance that is identical to maximal ratio combining in terms of the SNR. However, it is challenging to implement because this requires channel state information at the transmitter. But if that is available, we can implement transmit beamforming. We have computed the SNR for transmit, we have demonstrated the transmit beamformer, computed the SNR for transmit beamforming, derived the bit error rate expression with transmit beamforming, and also seen a couple of simple examples. Now, in the subsequent modules, in the next modules, we are going to look at what can we do when we do not have channel information, state information at the transmitter, and then we have to use space time codes or space time block codes, and this we are going to look at in the subsequent modules. So, we will conclude this module here. Thank you very much.